TiCoSS, a novel joint learning framework, integrates semantic segmentation and stereo matching tasks within a unified model, capitalizing on the synergies between these two key components of visual environment perception in robotic systems. By leveraging these synergies, TiCoSS enhances scene understanding and improves overall performance. The framework introduces three main innovations: a tightly coupled, gated feature fusion strategy, which adaptively combines task-specific features; a hierarchical deep supervision strategy, which guides the learning process through multi-scale supervision; and a coupling tightening loss function, which encourages the sharing of informative contextual and geometric information between tasks. These contributions lead to superior performance in both semantic segmentation and stereo matching. Extensive experiments on the KITTI and KITTI-2 datasets validate TiCoSS's effectiveness, demonstrating a notable increase in mean intersection over union (mIoU) of over 9% compared to previous state-of-the-art methods. This significant improvement highlights the potential of TiCoSS to advance the field of robotic vision. This section of the research paper delves into the limitations of existing joint learning frameworks for semantic segmentation and stereo matching. The current approaches, such as S3M-Net, face issues due to loose coupling between the two tasks, leading to subpar performance. Specifically, the feature fusion strategy employed in previous works involves element-wise summation of contextual and geometric feature maps, which can result in conflicting learning representations and erroneous segmentation results. Moreover, the deep supervision strategies used in these frameworks overlook the potential interactions among auxiliary classifiers, leading to limited improvement in semantic segmentation. To address these issues, the authors propose a novel approach: tightly coupled semantic segmentation and stereo matching network, TiCoSS, which focuses on enhancing the coupling between stereo matching and semantic segmentation. TiCoSS introduces three new techniques: tightly coupled, gated feature fusion (TGF) strategy, hierarchical deep supervision (HDS) strategy, and coupling tightening (QUART) loss. The TGF strategy utilizes selective inheritance gates to propagate useful contextual and geometric information from the preceding layer to the current layer. The HDS strategy uses the fused features with the highest resolution to guide deep supervision throughout each branch. The CT loss consists of a stereo matching loss, semantic consistency guided loss, disparity inconsistency aware loss, and deep supervision consistency constraint loss, which collectively advance S3M-Net and result in a new, powerful, and tightly coupled joint learning framework. The contributions of this article include the TGF strategy, HDS strategy, and the DIA loss and DSCC loss that tighten the coupling between the two tasks. The article is organized as follows: Section 2 reviews related prior arts, Section 3 introduces the proposed TiCoSS, Section IV compares the network with other state-of-the-art approaches and presents ablation studies, and Section V concludes the article and provides recommendations for future work. Joint learning frameworks that simultaneously address semantic segmentation and stereo matching tasks are crucial for improving performance in computer vision. Existing approaches, however, have limitations, such as requiring extensive annotated training data, complex training strategies, or pre-training on large-scale datasets. To overcome these limitations, a novel tightly coupled joint learning framework, TiCoSS, is proposed, which leverages both contextual and geometric information to enhance semantic segmentation performance. TiCoSS builds upon S3M-Net, with a focus on improving the coupling between semantic segmentation and stereo matching. The framework consists of a duplex, tightly coupled encoder that selectively extracts and fuses heterogeneous features from RGB images and disparity maps. A novel HDS strategy is introduced, which leverages fused features to guide deep supervision across each branch, and a CT loss that supervises the entire joint learning process. The tightly coupled gated fusion strategy, TGF, is designed to overcome the limitations of previous approaches, such as S3M-Net, which employed a simplistic element-wise summation to fuse features. TGF uses selective gates to complement contextual features with useful geometric features, resulting in a tightly coupled duplex encoder. This enables the features at each scale to be selectively fused, allowing the network to learn more effective representations for both tasks. The advantages of TiCoSS include its ability to learn semantic segmentation and stereo matching simultaneously, even with limited training data, and its end-to-end training fashion. Additionally, TiCoSS does not require pre-training on large-scale datasets or complex training strategies, and the source code is publicly available, reducing the risk of introducing errors during reimplementation. The proposed TiCoSS model presents a novel architecture for end-to-end joint learning of semantic segmentation and stereo matching. It utilizes a duplex encoder with a strategy called tighter geometric feature selective fusion, TGF, which aims to fuse geometric and contextual features more effectively. This is achieved through the use of selective inheritance gates, SIGs, which selectively inherit useful features from previous layers into the current layer, enhancing both the depth and spatial richness of the features. The TGF strategy also employs hierarchical deep supervision to ensure that the network learns to extract and fuse features effectively at different scales. The duplex encoder consists of two branches, one for processing RGB images and another for disparity maps. The geometric features extracted from the disparity maps are fused with the contextual features extracted from the RGB images using the SIGs. This fusion process is designed to reduce the noise and misguidance caused by indiscriminate feature fusion as the network goes deeper. The paper also discusses the importance of hierarchical deep supervision, which is crucial for the network to learn and extract features effectively at different scales. This is achieved by revisiting the deep supervision strategies employed in SNE-RoadSeg Plus and UNet 3+. The proposed model uses a multi-scale feature extraction and fusion approach, where the features are progressively fused and enhanced through the SIGs. This approach allows the model to leverage both deeper, semantically stronger features and shallower, spatially richer features, leading to improved performance in both semantic segmentation and stereo matching tasks. The HDS strategy is a proposed approach for enhancing the performance of a joint learning framework that simultaneously addresses semantic segmentation and stereo matching tasks. This strategy combines the strengths of two prior approaches by applying deep supervision to both the main and side branches, allowing the network to leverage features from shallow layers, rich in local details, and deep layers, semantically strong. The HDS strategy also utilizes a feature dynamic alignment, FDA, block to align channel dimensions and spatial resolutions between a pair of features at different layers, preserving fine-grained local details and enhancing the decoding process in the side branches. Furthermore, it introduces a coupling tightening loss function, which is designed to supervise both tasks simultaneously. This loss function consists of four components: disparity inconsistency aware loss, LDIA, deep supervision consistency constraint loss, LDSCC, semantic consistency guided loss, LSCG, and stereo matching loss, LSM. The DIA loss focuses on regions with semantic inconsistencies caused by occlusion and reflection, while the DSCC loss utilizes the KL divergence to measure prediction differences across scales and enhance the informativeness of features at different resolutions. The proposed CT loss function aims to tighten the coupling between the two tasks at the output level, significantly improving semantic segmentation performance across scales. The paper presents a comprehensive comparative analysis of various state-of-the-art, SOTA, semantic segmentation networks, including PSP-Net, DeepLab v3+, BIS-Net Segmenter, SegFormer, Mask2Former, MFNet, RTFNet, SNE-RoadSeg, OffNet, RoadFormer, S3MNet, and TiCoSS. This comparison is conducted on two datasets, KITTI 2015 and vKITTI 2. The qualitative experimental results from the KITTI 2015 dataset, as shown in Figure 2, demonstrate that TiCoSS outperforms other networks in terms of accuracy and detail, particularly in areas such as road markings and vehicle boundaries. Similarly, Figure 3 illustrates the qualitative experimental results on the vKITTI 2 dataset, where TiCoSS again shows superior performance compared to other networks, accurately segmenting different elements within the scene while maintaining a high level of detail. Quantitative evaluation of these networks, as discussed in the paper, highlights TiCoSS's superior performance in terms of various metrics such as intersection over union, mIoU, and mean average precision, MAP. These experiments aim to assess the network's ability to accurately segment objects in urban scenes, which is crucial for applications like autonomous driving and robotics. In conclusion, the experiments presented in this section of the paper demonstrate the effectiveness of TiCoSS in achieving high-quality semantic segmentation results, surpassing the performance of other SOTA networks on both the KITTI 2015 and vKITTI-2 datasets. This suggests that TiCoSS could be a valuable tool for enhancing the accuracy and efficiency of various computer vision tasks. The TiCoSS model is evaluated on two datasets, vKITTI-2 and KITTI 2015, and compared to state-of-the-art semantic segmentation and stereo matching networks. These datasets are chosen for their comprehensive annotations in both semantic and disparity, allowing for a thorough evaluation of the model's performance under adverse weather conditions and real-world driving scenarios. The vKITTI-2 dataset comprises 15 semantic classes, providing virtual replicas of 5 sequences from the KITTI dataset. Dense ground truth disparity maps are obtained through depth rendering using a virtual engine, with 700 stereo image pairs used, 500 for model training and 200 for validation. The KITTI 2015 dataset contains 400 stereo image pairs captured in real-world driving scenarios, providing 19 semantic classes consistent with the Cityscapes dataset. Sparse ground truth disparity maps are obtained using a Velodyne HDL64E lidar, with the data split into a 7:3 ratio for training and testing, respectively. Qualitative results demonstrate the superior performance of TiCoSS over existing state-of-the-art networks in both semantic segmentation and stereo matching tasks. The model effectively handles challenging scenarios such as adverse weather conditions and varying lighting conditions, outperforming its counterparts in terms of accuracy and robustness. The proposed model's ability to leverage both semantic and disparity cues to enhance its performance is evident in these qualitative evaluations, showcasing its capacity to accurately segment scenes and estimate depth in complex environments. The experimental setup for this research involved conducting experiments on an NVIDIA RTX 4090 GPU with a batch size of 1, utilizing the AtomW optimizer for model training. The maximum disparity search range was set to 192 pixels, and all images were cropped to 512 × 256 pixels before being processed by the network. Standard data augmentation techniques were applied to improve model robustness. 7 evaluation metrics were used to quantify the performance of semantic segmentation: accuracy, mean accuracy, precision, recall, mean F1 score, mean intersection over union, and frequency-weighted intersection over union. Additionally, 2 metrics were used to quantify the performance of stereo matching: average endpoint error and percentage of error pixels at tolerance levels of 1.0 and 3.0 pixels, respectively. The experimental results demonstrated that TiCoSS outperformed all other state-of-the-art single-modal and feature fusion networks across all evaluation metrics on both the KITTI and vKITTI-2 datasets. Specifically, TiCoSS achieved substantial improvements compared to S3MNet, the state-of-the-art joint learning method, on the KITTI dataset, with increases in mean accuracy, mean intersection over union, frequency-weighted intersection over union, and mean F1 score. Similarly, on the vKITTI-2 dataset, TiCoSS outperformed other networks across all evaluation metrics. The qualitative results also demonstrated TiCoSS's superior performance and robustness in complex scenarios, such as foggy and rainy conditions. In terms of stereo matching performance, TiCoSS demonstrated improvements compared to S3MNet, with increases in average endpoint error and percentage of error pixels on both datasets. These improvements can be attributed to the tighter coupling between the two tasks within the joint learning framework, resulting in more comprehensive geometric features with informative contextual information. Ablation studies were conducted to validate the effectiveness of the proposed TGF strategy and deep supervision strategy. The results demonstrated that TGF outperformed other state-of-the-art feature fusion strategies, with increases in mean intersection over union and frequency-weighted intersection over union. Additionally, the proposed HDS strategy achieved state-of-the-art performance across both evaluation metrics, with improvements in mean intersection over union and frequency-weighted intersection over union. The proposed TiCoSS model is comprehensively evaluated on two benchmark datasets, KITTI 2015 and vKITTI 2, for semantic segmentation tasks. The model's performance is compared to state-of-the-art, SOTA, networks, including PSP-Net, DeepLab v3+, BiasNet v2, Segmentor, SegFormer, Mask2Former, MFNet, RTFNet, SNE-RoadSeg, OffNet, RoadFormer, and S3MNet. Quantitative comparisons are presented in tables I and II, showcasing the superiority of TiCoSS over existing SOTA networks on both datasets. TiCoSS achieves an accuracy of 91.95% and a mean intersection over union, mIoU, of 63.91% on the KITTI 2015 dataset, and an accuracy of 98.69% and an mIoU of 88.46% on the vKITTI 2 dataset. Ablation studies are conducted to assess the effectiveness of the proposed components, including the feature fusion strategy, loss function, and combined use of novel contributions. The results validate the superiority of the proposed feature fusion strategy, which utilizes rich, fine-grained local spatial details from the shallowest layer. The ablation study on the loss function demonstrates that the DIA and DSCC losses make significant contributions to semantic segmentation. The combined use of novel contributions, including TGF, HDS, and CT loss, leads to the best overall performance. Furthermore, the results of the ablation studies on the selection of loss weights alpha and beta show that alpha equals 1.5 and beta equals 1.0 are the optimal choices, leading to the best overall performance. Overall, the results demonstrate the effectiveness of the proposed TiCoSS model in semantic segmentation tasks, highlighting its superior performance compared to existing SOTA networks. This section of the research paper presents a comprehensive comparison between various state-of-the-art stereo matching networks on the KITTI 2015 and vKITTI 2 datasets. The proposed TiCoSS model outperforms other models in terms of both EPE and PEP metrics, as summarized in Table 3. An ablation study on the feature fusion strategy, shown in Table IV, demonstrates that the proposed TGF strategy significantly improves the performance of the S3MNet model, enhancing both mIoU and FWIOU metrics. The authors also conduct an ablation study on the hierarchical deep supervision (HDS) strategy, presented in Table V. This study reveals that incorporating HDS leads to substantial improvements in mIoU and FWIOU, with the best performance achieved when all components of HDS are utilized. The selection of guidance features for the HDS strategy is investigated in Table V, indicating that the optimal combination of geometric and contextual features results in the highest mIoU and FWIOU values. Finally, the paper explores the effectiveness of different semantic segmentation losses within the CT loss function, as detailed in Table 7. The results suggest that incorporating all three semantic segmentation losses leads to the best performance in terms of mIoU and FWIOU. Overall, this section provides a thorough evaluation of the proposed TiCoSS model and its components, demonstrating its superior performance in stereo matching tasks and shedding light on the key factors contributing to this improvement. The research paper presents an ablation study on the three contributions of TiCoSS, a novel algorithm for joint semantic segmentation and stereo matching. Conducted on the KITTI 2015 dataset, the results are shown in Table 8, indicating that each contribution TGF, PGDS, and CC loss improves TiCoSS performance. Combining all three contributions yields the best results, with a mean intersection over union, mIoU, of 63.91% and a mean foreground similarity coefficient, MFSC, of 92.90%. The paper also discusses TiCoSS limitations, such as requiring both semantic and disparity annotations, which can be labor-intensive to collect. This has led to suggestions for future research directions, including semi-supervised or few-shot semantic segmentation, and self-supervised stereo matching. Furthermore, the authors believe that optimizing model complexity is necessary before deploying TiCoSS in autonomous vehicles. However, you haven't provided the content for refinement. Please provide the text, and I will transform it into a direct, concise form suitable for voiceover narration, following the guidelines you specified.